The problem we are addressing in this lecture is the following. If we are given two states, psi and phi, let us say they are qubit states, so they belong to the Hilbert space H2, and they are not orthogonal. It means psi phi inner product is not 0. Let us call it to be alpha, which is a complex number. Now, can we design a setup in which such that we can distinguish between the states psi and phi? So the problem can be stated like this. We have an ensemble of quantum systems, and each of that quantum system is either in the state psi or in the state phi. And when the quantum system is given to us, we need to tell whether the state of the system was psi or phi. If they were orthogonal states, then we could have chosen a measurement basis as psi and psi orthogonal, and then we could have easily tell whether the input state was psi or it's orthogonal. But here it is not the case. So the state of the ensemble, which has a 50% probability of getting state psi and 50% phi, the initial state of that can be written as a mixed state, half times psi in a outer product psi and phi. This is the initial state of the ensemble. Now we need to find an experimental setup such that we perform measurement and we get a click in the plus side or minus side, and by looking at those clicks we can tell whether it's a state psi or phi. There are some restrictions and some conditions of this whole measurement setting, that the result or the outcome or the distinguishability whether the input state was psi or phi can be probabilistic, but it should be unambiguous. So it means for a given input quantum system, we can say the state is either psi or phi, or the results are inconclusive. It shouldn't be that we call the state to be psi, but it was not psi. So that's ambiguity. So the result should be unambiguous, but it can be probabilistic. So the first attempt can be the following. Let us design an experimental setting such that the basis in which we are performing measurement is the psi and psi orthogonal. So if the input state is psi, then it will click in the psi, in the plus click, and if the input state is phi, then it can click in plus or minus. So from here we can see that whenever we get a click in minus, this is the minus output port, whenever we get a click in minus, then we know for sure it was state phi. But when we get click in plus, then it can be psi or phi. So from this measurement setting, we can be sure when it is when the click is in the minus, so we know it's a state phi. But when the click is in plus, then we do not know whether it was in the state phi or psi. And the success rate will be the psi orthogonal rho psi orthogonal. So whenever there is a click in psi bar psi orthogonal, then that is a successful case. This will be psi orthogonal phi mod. And this we can write as half phi psi orthogonal phi. We know that psi outer product psi plus psi orthogonal is identity. It means we can write psi bar as identity minus psi. Hence this can be written as half times phi minus psi mod square. So we get PS to be half times 1 minus phi psi mod square, which was alpha mod square. If we assume psi to be cos of theta over 2, sine of theta over 2, and phi to be cos of theta over 2 minus sine of theta over 2. This is just single parameterization of the two states, psi and phi. They are, you can see they are not orthogonal. In fact, psi phi is cos of theta. So alpha is cos of theta. And with this choice, we get sine square theta over 2 as our success probability. We will get the same result if we choose a measurement basis which is phi and phi orthogonal. So because there is basically no difference between psi and phi, and the success probability we get is sine square theta over 2 in such kind of situations. Now, till now we have employed only the projective measurement in a basis which will give us unambiguous result, but only with sine square theta over 2 success rate. Now, can we do better than this when we go to POVMs? So this is what we will explore next. Let us say we have an ancilla, and initially it is in the state 0, okay, and the total state of a total Hilbert space is system tensor ancilla. So our total state is psi tensor 0, or let me call psi tensor 0, or it is phi tensor 0. So the state is cos theta over 2, 0, 0, plus minus sine theta over 2, 1, 0. Because we can write psi and phi as cos theta over 2, 0, plus minus sine theta over 2, 1. So this is the psi initial of the system and ancilla. Now let us say we can find a unitary which acts as follows. If it acts as cos theta over 2, 0, 0, then it will give us sine theta over 2, 0, 0, plus root cos theta 1, 1. And if it acts on 1, 0, it will give us 1, 0. If it acts on 0, 1, it will give us 0, 1. And when it acts on 1, 1, we will get something orthogonal to this state. So let us say such unitary exists. Okay, we know it will work. That's why I'm giving you this unitary. Then we will examine this unitary later on. So what we have here is when we apply u on psi in initial, we get cos theta to cos theta to cos theta over 2, 0, 0 will go to sine theta over 2, 0, 0 plus root cos of theta 1, 1, and plus minus sine theta over 2 will go to 1, 0 will go to 1, 0. We can write it as sine theta over 2, 0 plus minus 1 cancels 0. These are the first two terms, first and last term, and the middle term cos of theta 1, 1, which can be written as 1 tensor 1. This 0 and this 1 is the state of ancilla, and this is the state of system. Now, if we perform measurement on ancilla, then we can get 0 or 1. If outcome is 1, then the state of the system collapses to 1, and we have no idea whether this 1 came from the psi or phi. If the ancilla is in 1, then system also goes to 1. But if the ancilla is in 0, then the system goes to sine theta over 2 is the overall factor. So we multiply with root 2 and divide it by root 2. So then the system collapses to 0 plus minus 1 over root 2. This is normalized state. And the plus sign is for psi and the minus sign is for phi. Now, if we perform, once we have 0 in the ancilla, then the system, we can perform the measurement on the system in the 0 plus minus 1 over root 2 basis. These are orthonormal basis. And then if we get 0 plus 1, then we know it was psi. And if we get 0 minus 1, then it was phi. So in that way, once the ancilla collapses to 0, we have already succeeded. Then we can figure out what was the state of what was the input state. So here the probability that the probability of failure is when we get 1 in the ancilla. So the probability of failure is cos of theta, and probability of success will be 1 minus cos of theta, which becomes 2 sine square theta over 2. If we remember that the probability of success from the projective measurement was sine square theta over 2, and that can be written as 4 sine square theta over 2 cos square theta over 2 over 2. That becomes 2 sine square theta over 2 times cos square theta over 2. So the probability of success, the sine square theta over 2, which we got from the projective measurement, that is a factor cos square theta over 2 smaller than the probability of success we got in this new method of performing measurement. So if we look at it carefully, what we have done is we had a system and we wanted to distinguish between the two non-orthogonal states of that system. We couple it with another ancilla, and the coupling unitary we found by some hit and trial method to be some strange unitary, and that unitary is giving us the probability of success to be a significantly larger number than the one we got from the projective measurement. It doesn't matter how we got that unitary, but that unitary is showing us that generalized measurements can give us results which are much better than the projective measurements. This is one example of showing the power of the projective measurements. Now, how to arrive at this thing? We can look at we can revisit our concepts of the POVMs. So let us say we consider a POVM with the first effect to be some number A times psi orthogonal, because we saw that psi orthogonal gives us the information about phi and phi orthogonal gives us the information about psi. So and there is no difference between psi and phi for us, they are on equal footing for us. Then we can assume the first effect as some number A times psi bar. We'll figure out what this A is, and the second POVM or second effect as A times phi orthogonal, and third is identity minus E1 minus E2. Now we have to choose A in such a way that E3 is positive, E3 is rank 1, and if we have those things, then we can figure out the success probability and stuff like that. Now psi we have chosen to be cos of theta over 2, sine of theta over 2. From here we can write psi bar, which is orthogonal to psi, to be sine of theta over 2 and minus cos of theta over 2. Similarly, phi is cos of theta over 2 minus sine of theta over 2. From here we can write phi bar to be sine of theta over 2 minus cos of theta over 2. We can check that psi bar is orthogonal to psi and phi bar is orthogonal to phi. So from here we can write E1 as A times sine square theta over 2 cos square theta over 2 sine theta over 2 cos theta over 2 minus and sine theta over 2 cos theta over 2 with minus sign, and 2 will be with plus sign. Same, just these off-diagonal elements are having different signs. So E3, which is identity 1001, minus E1 minus E2. So plus or minus a times, when we add these two, we get 2 sine square theta over 2, 2 cos square theta over 2, 0, 0. So we get 1 minus 2a sine square theta over 2 and 1 minus 2a cos square theta over 2. Now, hypothetically, our setup is such that, formally, our setup is such that we have our density matrix going in, and output are the three measurement outcomes, that is E1, E2, E3. We know when E1 click, and E1 was just psi orthogonal, then the input state was phi. When E2 clicks, which is the phi orthogonal, then the input state was psi. And when E3 clicks, that's the failure. So the probability of E3, that is expectation value of E3, will be trace of E3 times rho, and rho is half times psi plus phi. And it turns out to be, so the P3 will be trace of identity minus a psi orthogonal minus a phi orthogonal times rho, that will give us 1 minus a times half times psi orthogonal phi mod square minus a times half times phi bar psi mod square, and these two numbers are same, and these two numbers are sine square theta. 1 minus a sine square theta over 2 minus a sine square theta over 2. So total is 1 minus a sine square theta over 2. So this is the failure probability. Now, from here, we see that we can make E3 rank 1 by making either this element 0 or this element 0. So it means if we make a to be 1 over 2 sine square theta over 2, then we get E3 to be rank 1. And if we choose a to be 1 over 2 cos square theta over 2, then E3 is rank 1. We substitute both of them in this, then P3 becomes 1 minus sine square theta over 4 sine square theta over 2. There is no over 2 here because the half they cancel. So 2. And that is 1 minus sine square theta can be written as 2 sine square theta over 2 4 cos square theta over 2 over sine square 2 sine square theta over 2. This is 1 minus 2 cos square theta over 2. If we choose a to be 1 over 2 cos square theta over 2, then P3 becomes 1 minus sine square theta over 2 cos square theta over 2. That will give us 1 minus 2 sine square theta over 2. That will be cos theta, and that will be minus cos theta. So from here we can see that the choice a to be 2 cos square theta over 2 gives us a valid probability of, because probabilities cannot be negative and we are choosing theta to be in the range, that cos theta is positive. So this is not a valid probability, so we get the probability of failure P3 to be cos theta for a choice of a equals 1 over 2 cos square theta over 2. So the probability of success becomes 1 minus P3, which is 1 minus cos theta, which is 2 sine square theta over 2. This is precisely what we got when we chose that unitary, which looked strange at a moment, but it seems like that gives us the same result as we get when we use the POVM technique. So in that way, using POVMs, that too 3-outcome POVM, we can find a better distinguishability method of two non-orthogonal states, and the results are strikingly different from the one we had from projective measurement. We can implement here, if we just look at this POVM, what we used, it is very interesting that E1, which is A, which was 1 over 2 cos square theta over 2 bar psi bar, E2, which is 1 over 2 cos square theta over 2 phi bar, E3, which is 1 minus 1 over 2 cos square theta over 2 psi bar minus phi bar, that is just 0 0 with some coefficient, and that coefficient is, that will be 1 minus 10 square theta over 2. So from here we can see that we have three unit vectors which are not normalized. One is u1, which is 1 over root 2 cos of theta over 2 psi bar, u2, which is 1 over root 2 cos of theta over 2 phi bar, and u3, which is square root of 1 minus 10 theta over 2 0. With these three, we have these three vectors which are not orthogonal, but they have the property that sum over I, ui equals identity. So they form a POVM, this ui. Now, by using Neumark dilation theorem, we should be able to construct three-dimensional vectors which are extension of the u1, u2, u3 in such a way that they form an orthogonal basis. So omega I we can make as ui direct sum ci. Ci will be just a number because we already have two-dimensional vector. We want to make it three-dimensional vector, and in such a way we choose ci in such a way that these ui's wi's are orthogonal basis. And this remains an exercise. For this given set of ui's, find ci's in such a way wi becomes orthogonal basis. Now, if we extend our Hilbert space of two vectors, 2 dimensions to 3 dimensions, and perform measurement with wi in wi basis, then we will get the same result what we discussed in two different cases here. One with the unitary acting on the system and ancilla, and other in terms of the POVM. And in this way, we can use generalized measurements to improve the distinguishability of non-orthogonal states.